Entropy! Some things are just going to happen whether we like it or not. Take, for example, this reaction right here. This is the reaction of iron and oxygen, and iron and oxygen combine to form iron oxide. We call that rust. It's a problem we have all the time, isn't it? We have to keep certain metal things painted, otherwise they may develop rust. The paint keeps the oxygen from getting to the iron and thus causing it to rust. Unless we take steps otherwise, this is going to happen. And in fact, it releases energy when it does. A delta H of negative 1625 kilojoules. Whenever we have a chemical reaction like this one that will occur, and once it begins, it'll keep going without any outside interference, we call that spontaneous. So, the reaction between iron and oxygen to form rust is spontaneous. It will do that whether we like it or not. And unless we take steps otherwise, it's going to proceed and form rust, giving off energy in the process. Now, if we turn this reaction around and make it the reverse reaction, where we're causing the decomposition of rust to form iron and oxygen, we're going to get an endothermic reaction there. This much energy will be required to make that happen. So, do we simply say that spontaneous reactions are always exothermic? Not exactly. For example, ice in a room temperature environment will melt without our interference. That's an endothermic process, right? Energy going into the ice to make it melt. So what gives? What else do we need to determine whether something is spontaneous or not? The answer is something called entropy. Now, earlier in the video, I jokingly blamed all of my problems in my terrible, no good, very bad day on entropy. And that's because many times we think of entropy as the amount of disorder that we have present in the system. And rightly so. But another way of thinking of entropy is the amount of ways in which energy can be distributed. How the particles can have freedom to go in different directions. So you could really think of entropy as possibilities. Now you might be wondering, why the use of S? Why the use of S as the symbol for entropy? And many people have thought about this. It could be that E was already taken and therefore we could not use it for entropy, but some people have stated that the fellow that actually came up with the idea of entropy, whose name is Rudolf Clausius, had another scientist that he was honoring by using the S, and that scientist was Nicholas Sadi-Carnot. Sadi-Carnot's work had been studied extensively by Clausius for several years, so it may be that that's the reason why he used the S, to honor the man that he greatly admired. Now, for a practical look at what entropy is, you could think of a toddler. If you had just one toddler that you were in charge of, looking after, you could probably manage the disorder pretty well. But increase the amount of toddlers, say to 20 or 30 in the same room, and now you have greatly increased your chances of disorder. Trust me on this. So the toddler is like the particles that we see in chemical reactions. The more particles there are, the more opportunities there are for interactions, and the more possibilities, permutations there are, giving us more disorder in the process. Now, entropy always has a tendency to increase. This is given to us in our second law of thermodynamics, where we say that spontaneous processes tend toward greater entropy in the universe. So, the more particles you have in a system, the more things that develop as time goes by, the more disorder there's going to be. So, just to put it simply, things tend to go from order to disorder. Now, do you remember how we said that a change in enthalpy or heat energy can be determined by taking the enthalpy of the products and subtracting the enthalpy of the reactants? Well, we can do the same thing with entropy. the change in entropy is equal to the entropy, or the disorder, of the products minus the entropy, or disorder, of the reactants. So, if we have entropy of products that's greater than entropy of reactants, our change in entropy will be positive, increasing disorder. If, however, the products have less entropy than the reactants, that means we have a change in entropy that's negative. In other words, less disorder. Now let's talk about ways in which entropy will increase. Entropy will increase when, for example, the substance changes from a solid to a liquid. Think in terms of that kinetic energy being greater and those particles being in greater motion. More opportunities for disorder. Also, when the substance changes from a liquid to a gas, you will have greater entropy in that case as well. So we can sum this up by saying the entropy of a solid is less than the entropy of a liquid, is less than the entropy of a gas. This also works, by the way, when you dissolve a solid into a liquid. By dissolving that solid, it's like you're freeing it. You're allowing it more opportunities and more disorder in that case. Now, I sort of mentioned this already, but I wanted to point out something, and that is that entropy is directly related to temperature. Did you hear me before mention kinetic energy and how when the kinetic energy increases, the entropy increases because you have more opportunities for disorder? That's temperature. So, whenever temperature increases, the entropy increases. When temperature decreases, the entropy decreases as well. You can also increase the entropy in a system if you increase the amount of gas particles in that system. For example, here we have ammonia gas breaking down to form nitrogen and hydrogen gases. Notice that there are greater amounts of particles in the product area than there are in the reactant area. We only have 2 moles of reactants, but we have 1 plus 3, 4 moles of products. So since the products have more particles on their side than the reactants do, that means we have a change in entropy that's greater than 0, which tells us that we have an increase in entropy. Entropy also increases when you increase the volume of the reaction vessel. Think of it this way. Remember those toddlers I talked about earlier? Let's say you have 20 toddlers, but you have them confined in a good-sized playroom. Then, let's take those toddlers and disperse them around Disney World. Much bigger volume, right? A lot more opportunity for disorder to take place. Increase in entropy. Now, just to restate, entropy decreases when you have a lowering of the temperature, the kinetic energy. When you go from a gas back to a liquid back to a solid. Or when you dissolve a gas into a liquid, you also decrease the entropy because you've essentially decreased the amount of kinetic energy that that gas contains. Think of it as you can run faster in open air than you can run in a swimming pool, right? Less kinetic energy. And so because of that, less entropy. Okay, let's see how you do. Let's play Which Entropy is Greater? Brought to you by the letter S. Okay. Which one's greater? Is it the entropy that we find in 10 grams of H2O in the solid state, or 10 grams of H2O in the liquid state? 10 grams of H2O in the liquid state. Correct. We have greater amounts of movement in the liquid state than we do the solid state. Greater amounts of movement, greater entropy. What about this one? 4 moles of gaseous HCl or 2 moles of gaseous HCl. Which has greater entropy? That's correct. The 4 moles of gaseous HCl. Greater amounts of particles gives greater opportunity for disorder. Contestant number 3. What if we have 2 moles of HCl gas at 300 Kelvin and 2 moles of HCl gas at 400 Kelvin? Which one has greater entropy? That's right, the 2 moles of HCl gas at 400 Kelvin. Am I delaying too long on waiting for your answer? Are you getting it right away? If so, I apologize for insulting your intelligence. Last one. What if we have 2 moles of HCl gas at 300 Kelvin in a 10-liter vessel and 2 moles of HCl gas at 300 Kelvin in a 5-liter vessel? Which one will have greater entropy? Have I given it away by the back and forth? Yeah, my bad. But anyway, you're right. It's this one right here. The 10 liters will give more room, more space, more opportunities for disorder. So there you go. Good job. Now, if you happen to break an egg, you're not going to be able to return that egg to its original state. Or if you cut a branch off of a tree and just lay it on the ground, well, that branch is just going to decay and wither away. It's not going to reverse and become a new tree or become more orderly without some assistance. So we know from the second law of thermodynamics that in a spontaneous process, entropy must increase. Did you catch that? If the entropy is increasing, it goes hand in hand to say that it's a spontaneous process. So what factors will give us that increase in entropy, that increase in disorder of the universe? Well, we could say that an exothermic system, a system in which the heat energy, the enthalpy, decreases, that means that the system is releasing energy to the surroundings, causing the surroundings to have increased disorder. That helps. Or if we have the entropy of the system itself increasing, if the disorder in the system is increasing, that helps increase the disorder in the universe as well, which means spontaneity. Now, a fellow back in 1878 named Willard Gibbs came up with this equation called the Gibbs free energy equation. This equation will tell us whether a reaction is indeed spontaneous based on the sign of this, delta G, which is free energy. Free energy is energy that's available to do work. Now, by contrast, some of the energy that's involved in entropy is dispersed in such a way, distributed so that it's too random. It's unable to be recovered to do meaningful work. How do enthalpy and entropy relate to free energy? And how do we know if a reaction is spontaneous? So again, let's use what we know about these factors that help the entropy of the universe, and let's plug them into our equation and see what happens. If we have a negative delta H, an exothermic reaction, and we have a positive entropy, notice what happens. We have a negative minus a positive. And if you're wondering about temperature, remember temperature in Kelvin for us can only be positive. So we have negative minus a positive, which is always going to give us a negative. So what that tells us is if delta G is negative, that reaction is spontaneous. Likewise, a positive value of free energy will mean that the reaction is non-spontaneous, that it's not going to just proceed without help. Okay guys, so here's our problem for the day. It involves this free energy equation we just talked about. And I want to find the free energy of a system, a reaction, in which the temperature is 382 Kelvin, the entropy of the system is 322 joules per Kelvin, the enthalpy, the heat energy of the system, is 145 kilojoules. Got to make sure we get that to where it's consistent, right? So let's watch out for your units there. Compute the free energy. Finally, tell me whether or not that reaction is spontaneous or non-spontaneous. There you go. Hey guys, that's it for the day. We've learned quite a bit. We talked first about spontaneity, the idea that you can have a reaction or a process that proceeds on its own without any outside interference. And then we also talked about entropy, the concept of disorder, how energy is distributed randomly at times. And then it got us into a discussion of how spontaneity and entropy are related. And that's through the second law of thermodynamics that tells us that in a spontaneous process, the entropy of the universe will increase. Then we talked about how entropy increases or decreases depending on condition. And that finally led us into Gibbs free energy, the equation that tells us whether or not a reaction is spontaneous or non-spontaneous. Look at that, you're done with chapter 15. That's amazing. Good work. Just one thing left to do, that's a test, but I have complete confidence in you. I know you're going to do fine. If you have any questions at all, give me an email. Don't hesitate to do it, and I'll be happy to help you. Guys, it's been fun. Until next time, God bless.